Okay, so let's get going. The first set of notes are out from what I understand this morning. I got emailed this morning. So have a look. There's a GitHub for that, right? So I don't know how we're going to mediate this. I guess Favonia is going to take pull requests, right? How are you going to work on updating them? Just the authors?
You need the ID, the
Yeah.
GitHub account.
Yeah.
And I can add them as the collaborator.
Yeah, okay, that'll be good.
Have
Yeah.
the access.
Because then we can kind of do this all as a community process, because there's no doubt as we go along there'll be corrections or modifications you want to make. So don't hesitate, especially on your own set of notes, if you want to update them later or something. That's good because it's nicer to keep things in a somewhat polished form. So that'll be good. And Favonia is organizing the prioritization because some of you are taking the class for credit, and so those people will be getting priority over people who are not, because for the obvious reason. So he's trying to sort that out. So that's what's happening right now. Okay, good. So that was like some admin thing. I think those are the only things that I have on the top of my mind. Okay, so what I was in the middle of doing, you remember, is I first looked at logic from the point of view from the point of view of provability. And we took care of that. We were looking at that where we had the idea of judgment A true, and we looked at order structures that we get like from Heiting algebras that work like that. And now what we're doing is I'm developing the idea of logic with proofs, with proofs involved in the structure. So we're looking at first having the idea of proof terms, and then we're going to develop the idea of sort of proof terms as maps. That's a certain idea. So this is where we got to the structure of these lattice structures like Heiting algebras, and here we're going to get to the structure of certain categories, which will be, in this case, what we're doing by Cartesian closed categories. And I'll show you how that develops here. And there's going to be some auxiliary notion that is new and that I'll be talking about today, which is the idea of definitional equivalence, which will be related to the idea of two maps being equivalent in the definition of a category, because here now, when we have proofs, we have to worry about, to some degree, as I'll make plain, I hope, in a moment, what are the what I'm broaching here is the issue of the identity of proofs. And the identity of proofs will raise some interesting questions for us, and they're going to motivate some of what comes along next when we start talking about dependent types and the interpretation of equality in particular. We will spend a lot of time on that. I originally thought I might talk about proof normalization today, but I decided to push that off because we have a little break, because next week I'm away at a conference and so is Favonia. So I'm going to develop this connection here, and I will come back. I owe you something about proof normalization, and it will end up being an analysis of this notion of equivalence. So that's what we'll do. I'll pick that up next week. Okay, so that's like the roadmap. This is where we are, and it's all by way of motivating some particular things, in particular this idea of equality and the notion of definitional equality are going to be very central to everything we do later in the semester, so I want you to know where this comes from. So the idea is that we first looked at the, if we're looking at the notion so let's look at the idea of proof terms. This will be our first thing, and what we're going to do is we're going, as I said at the very end last time, the first way we're going to look at this is we're going to think of it as labeling our hypotheses, because we're now interested not so much in whether A has a proof, but that M is a proof of A. So this is going to be a grammar or a notation or a language. So this will give us I don't know how many M's I need there, grammar of proof, okay? So the idea is I'm going to have some notation that I'll write down which represents the proofs that we're studied so far. We're just doing intuitionistic propositional logic, in order to broach all of these subjects in a way that is like completely, I hope, very easy to grasp. And then I will use that same architecture to talk about dependent types, which will then get us going to get us into a bunch more complications. Okay, so the first thing is we're going to have the notion of the grammar of proof. And I mentioned at the end last time that you could think of these as hypotheses or names for hypotheses, but what is really important is that they behave like variables, okay? So this is the idea. And why do they behave like variables? Because we can revisit the structural properties from the point of view of this grammar of proof terms, and we will see that when we do that, that they do behave like variables. So in particular, we can have the following thing. We can have sort of the reflexivity, which might now also be called the variable rule, which says that if I declare some variable, and let me write it out in this form, then I may use that variable. So it's just exactly the re-expression of reflexivity, which I've built in some weakening and exchange here. Don't worry about that right now. But I just want to say that if you have a variable, if you assume that x is a proof of A, then you can use it as a proof of A, obviously enough. And let me skip to the most important one, and then I'll talk about the other structural properties. So this would be transitivity, or now it could be called substitution. So we could call this the variable rule, and we could call this the substitution rule. Okay, either one. And it's just a matter of rephrasing it. So we can say something like this. For example, if I have a scenario of this form, and I also know that M is A, then I will know with gamma and gamma prime that I have this notion of substitution. M for xn is B. And this is going to be defined to be substitution. And so this is just what you learned in school, basically. Variables are unknowns, and you plug in, they're given meaning by substitution, and you plug them in. Now here's something you can go look it up. What is the definition of substitution? I'm not going to spend a lot of time on this, so you should, if you don't know anything about this, you should look this up, like in my book on programming languages, or any of 100 other sources, and get the definition of capture avoiding substitution. We'll get back to the issue of capture in a minute when I talk about binding operators. I'm not going to go into the details about that. So now there's looking at like weakening. What does weakening mean in this setting when it's spelled out with proof terms? Well, it simply says that one way to formulate it is, if I know something like this, then on the basis of any other bunch of variables, I still know that fact. So I can introduce new variables that are apparently not needed, because I was able to derive this judgment without these variables, and then I can just throw them in after the fact. And then there is contraction, which we talked about before. And contraction could be seen as, in fact, there are different ways of organizing these things. It could be seen as something like substitution, except that it's all about variables. So in particular, if I do this, if I have two variables, let's write n and b here. If I have two variables, x and y, both of the same type, or that is referring to unknown proofs of propositions A, so I'm foreshadowing what I'm going to say in a few minutes. So if we have two unknowns, x and y, but they're unknowns of this unknown proofs of the same proposition, then I can contract them, and I can just have one. I'll call it z here. And then what do I do? Well, what I'm going to do is, the reason I can contract them is that I'm allowed to replicate the variable for x and y in n, and get myself a proof of B. So when spelled out with proof terms, it's sort of especially vivid, I would say, that you can see that the meaning of the contraction is I can do the replication of the variable. Okay, I can, or here it's a duplicate, I can do this replication of the variable. I can duplicate the variable like that. Okay, and then there is exchange. Oh, and exchange is very unpleasant to write, so I'm going to use it I'm going to use a little notation. So I can write it like that. And now if you'll let me do this, I'll write it like that. This is supposed to be, so pi is any permutation of whatever 1 to n, which is the 1 to the length of gamma, the numbers in there. Well, this is a little cheating, but anyway, you know exactly what I mean. What I want to do is a permutation of actually the variables x1 through xn you permute all those bindings. Okay, that's the idea. That's actually not a very good way to write it. Oh hell. All right, now that I think about it, that's not a good way to write it. All right, let me write it this another way. All right. So you know what I'm going to write, but let me just do it properly, and then the idea is I can permute these things, so I can write. Oh, they don't have to be the same at all. B x a gamma prime. Oh, damn. All right, C. Now you know why I complain and I want to write that one down. Okay, good, because I invariably get it wrong. Okay, so the order doesn't matter. Okay, so that's the idea. So I just wanted to revisit. Those are what the structural properties would be with respect to when I write down the proof terms explicitly. So that's important. And now if I continue to write down those proof terms, then what I'm going to do is let's revisit the rules, like for example, for the various connectives. So let's look at how we'd rephrase logic in this setting. So one thing is, now I tend to write the gammas a lot. Remember we had the idea that truth was the trivially true proposition. So I need a notation for the proof that it's trivially true. So I'm going to write it like that for reasons that will become clear in a minute. You already know, I think, many of you, but I'll just play along. Okay, so that will be the notation that I have for. Right now, I want to say that's the notation for the trivial proof of truth. It's the null tuple, or empty brackets. And now, what did we do before? Oh yes, so if we had conjunction introduction now, what do we do? So we say if M is a proof of A and N is a proof of B, all I'm doing is transcribing what I said before. Then I need a proof of A and B, and I'm going to write that like this. Okay, and so that'll be the notation. To some degree, it's arbitrary, but I'm using conventional notations. So this is andolim 1, and I'm going to have andolim 2. I want to write these down because I want there's something I need to get across to you. So I want to make sure I do this right. So we do this. So first of M is A, so I'll call that, the notation I'll use for that is first of M. And if I do this, A and B, and then I'll do second of M, which will be B. And let me write down just the negative fragment as a starting point, and then I'll come back to the positive fragment later. So I want the implication introduction, and the idea is I need a proof term for an implication. A implies B, and so the idea is if I wanted to deduce A from B, I introduce a new assumption, and I get a proof of B, and then I wrap that entailment up into a little notation, which is lambda xm, written like that, so you'll know that, you've seen that before. And then the implication elimination says if I have a proof of an implication, and I have a proof of the antecedent, then I can combine them. Maybe I'll write them M applied to N as B. Okay, and there's various other notations that people use. So this is for the negative fragment. I'll come back to the positive fragment a little bit later. Okay, so these will look familiar to you. Okay, so now the reason we introduced these things before was the reason we got into the business of writing down proof terms is because we wanted to talk about make a nice way to talk about Genson's inversion principle. And that was all by way of, well, two things. Remember, the idea was, well, many things to be said here. The idea was that elim is post-inverse to intro. That's the general, sort of the general idea of what is meant by the inversion principle. And what it does is it gives a dynamics of proof. So we have this gives us a dynamics of proof, should have said of, a dynamics of proofs, a way to run them. Okay, that's what we're going to do. So I'm going to explain that using this notion of definitional equivalence. So that's why I'm using that. So we get a dynamics of proofs. And then a little bit later, we're going to use that, the inversion principle, we're going to characterize definitional equivalence classes in a certain way so that we're able to prove later, we'll use this as the basis for proving, for example, for doing proof theory. So for example, proving the disjunction property, which I mentioned before, which implies that the law of the excluded middle is not always valid. not always valid or not always derivable. That's what we were talking about last time. So I was saying I wanted to draw the distinction between it not being always derivable from it being refutable. We talked about that, okay, but we left open a proof that you can't really derive the law of the excluded middle. So we were going to do that by proving the disjunction property, and for that I'll need an analysis of this thing. So the way I'm going to phrase the inversion principle is through the concept of what is called definitional equality. And if you haven't studied constructive type theory or related topics before, then maybe you've never heard of definitional equality as a concept in and of itself, because in traditional formalisms like first order logic, predicate calculus, or in pencil and paper notations that people use, no one ever draws a distinction between what I will eventually call propositional equality and definitional equality. That is, that's what is going on here. So there's an important thing that comes up that's related to the computational meanings of proofs and the dynamics that I'm explaining here. So we could look at this. This is where we get computation from. Okay. So my view in all of this is that computation comes from Gensen's inversion principle. That's the core origin of computation. So that's what I'm doing. And so definitional equality is central to explaining that. With things like first order logic or other such axiomatic theories, you don't have any dynamics at all. And then this kind of issue can get swept under the rug to a certain degree. But as we're going to see by the end of this lecture, there are some subtleties about equality, and I'm going to start bringing those out because those are what motivates a lot of what will follow. Okay, so let's do this. So what do I mean by definitional equality? Well, it's hard to give a definition of it's easy for me to give you a formal definition of definitional equality in a particular logic, like the negative fragment intuitionist propositional logic. I will give you an inductive definition. There will be no question about what I'm defining. But it's not so easy to say, like for an arbitrary logic, what exactly should definitional equality be? And so that's, I'll come back to that topic a little bit later. Right now, though, I'm just going to give it as a definition. So basically what I'm going to do is I'm going to end up saying it's the least congruence containing the following rules. You know, closed under, what I mean by closed under, you could say closed under the following rules, okay? That is, the following rules are valid. What do I mean by least congruence? What I mean is it's an equivalence relation, so it's reflexive, symmetric, and transitive, and it's compatible with everything. And what do I mean by it's compatible with everything? Well, before I get down to the rules which are going to follow, what do I mean by compatible is what I mean by is the following kind of thing. Is, for example, take first, for example. So we will say if M is equal to N in A and B is what it should be, or how about if I write M prime, then first of M is definitionally equivalent to first of M prime in A, as it turns out, and then I will say, etc. That's what I mean by compatible. Okay, so, or that it's a congruence. That is, everywhere you see, you can replace equals by equals. So all of the operators respect definitional equality. So you could say that's where the word compatible comes in, or you could say that the operators respect definitional equivalence. And that's true for all of them. Okay, so I can replace M by M prime, definitionally N by N prime, etc. Everywhere you think you can do this. So all I need to now do is show you what are the key rules, which are the actual content of Gensen's inversion principle. And so all we do is this: it's nicer to write it down using proof terms now. So let's look, for example, you can see what we're going to do. So here's one. One of them says, under suitable assumptions, okay, which I'll write down. If I take the AND elimination, if it is up against an instance of AND introduction, then you should be able to simplify and get a proof of A, given that in this case M is in A and N is in some B, and I don't care what B is because I'm projecting from the pair. Okay, so the B is arbitrary. The N and the B are completely arbitrary. Well, they're all arbitrary, but anyway, the thing that's relevant at the bottom of the line is the M, which is A. And under similar, so the point is it's elim cancels intro. And under similar assumptions, we have that elim cancels intro in the other scenario, the other elim up against the other intro. So that will look like that. So that's one of Genson's principles. You could write these all out using derivation trees. You know, I could draw pictures like I did before. You know, if you derive, you know, this will be my M, right? And this is A, and I derive N, which is B, and then I put them together and I get A and B, or the pair A and B, and then I do first of that. Okay, this is what it would be in a picture. Then I can say that is somehow, by Genson's principle, turned into this derivation M of A. You can do it like that. That's what Genson originally did. That's the way the notation, you will see it in older sources, like going back to the 30s or 40s. But this is a little more, you know, nicer to write it down in that form. But that's what I'm doing. I'm just saying if you did an introduction followed by elimination, well, the whole thing's kind of ridiculous because you could just cancel out all this junk over here and just use that, and you didn't need to go through all this extra trouble. Now you might wonder, how could that be interesting? Well, the reason it's interesting is in conjunction with, like you might say, yeah, this is a perfectly reasonable simplification, but how idiotic can you get? I mean, why would you ever have written this down to begin with? Okay? It's like that's what you would think. Well, you might think that, except until you realize that there is the structural property of substitution. And so the point is, I might have written down a proof here, M, which is as pretty indirect as you possibly could be. I will give a definition of that later. I will say it's a canonical proof of A. So we'll just use that word. So let's say M is canonical. It doesn't have any of this nonsense in it, okay? And N is canonical. It doesn't have any nonsense in it. When you plug M in for N, you could very well have nonsense in it. Because why? Because you could have the N in question could be X applied to some P. Oh, well, we're going to get there in a minute. Well, let's try it differently. It could be first of X, so that I can use this as an example. And then M is as nice as possible, could be the pair Mn, and it's as nice as possible. But now when I substitute, then I will end up with first of the pair Mn, and now I have to simplify. So it's not idiotic, okay, that you would put in these simplifications, because when you're doing as soon as you do substitution, then you can take canonical things and canonical things, and when you substitute them in, it's by no means canonical. That has an indirection in it. So I can get rid of all these indirections. So that's why I care about getting rid of all those indirections. Okay, that's why it's not like just a dumb thing. Okay, and so that's good. So think of it like any program you've ever written in any programming language, right? Whatever the programming language is, in some form or another, no matter how it's said, there's a variable representing the input. Okay, you write down the program does not run. Okay, your C program has main, has argv and argc in it. Okay, those are some variables. There's nothing to do. Main is just main. Okay, now you plug in two strings for argc and argv, and now you can run it. Okay, so the dynamics applies. Right, the proof simplification applies. So it's the same. Okay, there's no difference. Okay, so that's what's going on. So that's why these are not like completely like silly. Okay, even though when looked at in isolation they look silly. Okay, this is what we do. So that's the first intro in elim. With truth, there's no elim, so there's no reduction rule is possible. And the other thing I have to do is implication, because I'm only doing the negative fragment right now. And so what I have to do is under suitable assumptions. If you prove an implication by a deduction of B from A, and you then turn right around and apply that to a proof of A, this is my lemma, then I can simplify that by just replicating in here and writing B. Okay? So in compiler jargon, this is called inlining. Okay? And if you weren't worried about the practicalities of, writing down proofs, you could, in principle, inline all the lemmas, right? We don't ever need the lemmas. We can always reprove them every time we need them, even if we appeal to them twice, well, you just prove it again. And so what this is doing is saying to do that. Okay? In principle, of course, that's possible. In practice, it would be unbelievably unbearable, but I'm not, okay, that's true, but anyway. Okay, so this would be, again, the cancellation principle of the elimination is post-inverse to the introduction, because this is the outermost form is an application, and the thing it's being applied to is a introductory form. So we get that cancellation. So for the negative fragment, that's what we have. That's the notion of definitional equivalence. So this gives us a notion of computation because we can compute by calculation with closed terms. That is, ones without any free variables. So if I have a term, m, which has no free variables, I can compute with it like you did in school and deduce that m must be equal to n. So that when you learned in school about polynomials, you probably found it really fun to manipulate polynomials when you first learned about it. And the way you did it was you wrote down one polynomial and you showed it's equal to another one. Or you took a polynomial and plugged in a number and then showed that it's equal to 17 or whatever it is. And so it's just a computing process. You wouldn't be sitting in this chair if you didn't enjoy that. So you must have enjoyed that back when you did that when you were a kid. So this is what's going on. It's like computing by calculation. Okay, so that's the story for the negative the negative fragment. Okay, and I want to say something about the positive fragment. But before I do that, in order to I thought it might be better if I interweave a discussion that I want to do here. I want to say now that we've developed at this point our first type theory. Okay, and I'm going to explain why do I say this is a type theory and where did this notation come from, and I'll come back to the positive fragment in a minute. Where did this notation come from? Well, it's based on the following idea. Once I have written down what the proof terms are, so we've got them on this board, and once I've imposed, there's one other thing I need to discuss before I say what I was about to say. I've imposed this kind of dynamic, so that's the Genson's inversion principle. Sorry, I lost my thread. So I want to mention one other thing, and then I can say what I was going to say. Sorry about that. Let me hold that beginning remark in abeyance. Which are another thing, which are called, these are also studied by Genson, which were Genson's the unicity principles. Which tell us something about the uniqueness of these map, and I'll tell you, and I'll show you what those rules are, and I'm going to then relate them to another formulation of what I've written down. So the idea of the uniqueness principles is, one way to say it is the other way around. One way to think about it is, let me just check for myself what I've got here. Okay, I'll get back to that. Okay, the uniqueness principles. One way to say that, all right, okay, one way to say this is, well, I'll just write down what the rules are. The way to say this is that the other way around. You could look at this as kind of the intro being post-inverse to the elim. It's the other possible relationship between intro and elim. We think of those as kind of mutually inverse. So the unicity principles are going to express them. And I'm going to write them down in the way they're usually written down, and then we'll see. Oh, right, so here's what I want to say. So this rule is often called, I'll write it beta for an sub 1. This is beta for an sub 2. So these are often called the beta rules. Okay, so this is called these are what are called the beta rules. For historical reasons. Okay, so these are the beta rules. So these are called beta for conjunction 1, beta for conjunction 2, and this is called beta for implication. And these are called eta rules, okay, the unicity principles, and now I'll write them down what they are. So the eta for truth, it says that, yes, it says that if you have any term of this type, it can only be the null tuple. Like that. That's the eta rule for truth. The idea being that there's only one way to write down a proof, and whatever you did, it might as well be considered to be equal to this. I'm going to amplify this point in a minute, but let me write down what the rules are. Then there's an eta for conjunction. And it says, if you give me anything, any proof at all of A and B, it can be thought of as having the form of a pair. Okay? That is, it can be put into canonical form, or the introductory form can be put into introductory form by saying that M must be equal to some pair. And what pair would that be? Well, it has the flavor of now intro being post-inverse to elim, which I'll say is the pair first of M and second of M. There's going to be another way to say these things in a minute, and I'll get to it. Okay, so that's the eta rule for conjunction. And then there's the eta rule for implication, which says that if M is if M is a proof of an implication, it can always be put into standard form definitionally by saying it's equal to lambda x mx in A arrow B. A implies B. And this should have said in A and B. Okay, written like that. That was the eta for wedge, for conjunction. Okay, those are the unicity principles. Okay, good.
The premise of the first one, should that be true on top?
Did I make a mistake? What?
It's just the top instead of.
Truth, yeah.
And on top, though, the premise. The premise of that rule.
Oh, yeah. Yeah, right, sorry. I got discombobulated. Okay, yeah. Yeah, clearly. Okay, so, all right, so those are the Genson's uniqueness principles, unicity principles. Now I want to study them, okay, a little bit better from what is called the great correspondence, the propositions as types correspondence. So the idea is this, is that there's a reason I've chosen all this notation, which I'm going to explain in a minute using the terminology of category theory. So that's what I'm going to do. And this comes up, and this is going, and it's based on the following idea. The notation I use for proof terms is based on the following correspondence between the forms of proposition on the left and the form of type, where we think of a type as classifying data. So the trivially true proposition is going to correspond to a type called 1. The conjunction is going to correspond to what is called their Cartesian product. So these are both products. So these are the finite products when taken together. This should sound familiar because when we looked at the Heiting algebras, we had finite meets. So we'll write that. When we have implication, that will correspond to the function space, which is also known as the exponential, e to the a, written like that. And then I'm going to amplify, I need to write other things down in order to get to this part, but I thought I'd give you a break and work in this in the middle. If I'm going to end up with falsehood corresponding to 0, which is sometimes, this is called, by the way, this is usually called a terminal or final object. This is a product. This is called an initial object, and I'll explain what that is. And then we will have the disjunction corresponds to the coproduct. And so this is the coproduct, so we get finite coproducts with exponentials. So that's the description we have so far. So on the Heiting algebra side, this corresponded to meets that we had when we weren't concerned with proofs, but only with provability. And these were the joins, so that's our lattice structure, because there's always going to be an entailment, and I'll explain that in a minute, and this corresponded to the exponential. Okay, so that's the picture we have. So what I'm really going to be doing, what I'm going to do next, is I'm going to generalize the story about the algebraic interpretation by considering proof terms to be maps. And that's the idea. Okay. So this is the great correspondence, and the correspondence is not merely based on, they kind of look the same, or that I, deftly chose notation to make it look good. I want to say that these, the inversion principles and the unicity principles together will make a very precise correspondence by looking at their structure from the point of view of a category. So what I want to do is want to have the notion of a category, which we can think of as a general, one way to think about it, there are many ways to think about a category. One way is to think about it as a kind of generalized preorder, that's a weird way to say it. Or you could say, in the sense that it's a preorder You can say it's a preorder with evidence. Okay, this idea of a something with evidence is going to come up again when we talk about groupoids a little bit later. So we'll get to that. So it's the idea of a preorder with evidence. So your first cut would be, if you think about it, whereas in a Heiting algebra we have just that A entails B, or A is less than or equal to B. Now we're going to have a reason why that A is less than or equal to B. And that's going to be the form of evidence, and that is typically written not less than, because the less than is a proposition that either holds or doesn't. You think of it as not having evidence. So if you want to look at the evidence, then we think of it as a map, that M is a map from A to B. Okay? So this is the idea. So we have as a primitive the notion of a map from A to B. I'll write it as M as well. And that there are some particular closure conditions. So you remember that before we even talked about meets and joins, we needed to have, well, at least a preorder or maybe a partial order, okay, depending on the exact definition of what you take as a Heiting algebra. And that distinction is connected with the principle of univalence we're going to talk about later. Because the difference between a preorder and a partial order is with a partial order, you say, well, if I have maps in both directions, then we'll consider them to be equal. This is an instance of univalence, actually, which is something that's one of the axioms of homotopy type theory, as I mentioned to you before. You're identifying things that are related in some symmetric manner. I'll get back to that a little bit later. So over here, what the idea of a preorder is that we have reflexivity, that there's maps, the identity goes from A to A, and transitivity, okay, which says if I'm going to do G after F, so that's going to go from A to C, if what? G goes from A to B, F wants to go from A to B, excuse me, G goes from B to C, and F wants to go from A to B. So you do G after F. You do F, which goes from A to B, and G from B to C. Then we get G composed with F, which looks like that. So that's the analog of the preorder structure. The preorder structure is the existence of identities and compositions. But just like we had equality over here for proof terms, these have to satisfy some coherence conditions. And what are these coherence conditions? Coherences are going to cause us a lot of grief, actually, a little later. Okay, so that's why I want to broach the subject. What are the coherence conditions? They are the following. These are very simple. There are the unit laws that says if I do the appropriate identity after F, that's the same as F at whatever type it's supposed to be. Okay, there's some A arrow B. Okay, A arrow B, so this would be identity of B. And F after identity of A wants to be F, which is also from A arrow B. So these are written like that. And then we need associativity, which says that if we have GH, that should be the same as FGH at the appropriate type, like some A arrow D or something. Okay, I have to write that what down as the appropriate type. I'm going to say something about that in a minute. In fact, I can draw a picture for you. I think I'll draw a picture here. So we have the unit laws and we have associativity. Did I miss anything? Is there supposed to be another law, Ed? Am I missing anything? Those are the laws I need, right? Okay, yep. Okay, sometimes, yeah, no, with the groupoid I have additional structure, okay? So the one that's interesting to look at is the associativity, because I can draw a picture. So we have this situation like this, okay? So we do H, G, F, right? Like that. That's the setup we have. We're doing G after H, and then we're doing F after that. So we have a picture that looks like that, right? So we have three things. And the idea is that because I have a binary composition, I can think of this as, so this is G, F after G, goes along here. And what goes along here is G after H, right? Okay, goes along here. So now I have this guy, which is, this is F after G after H, if I said it right. And then this guy is the other association, F after G after H. Okay, written like that. Okay, so that's the the picture of what's going on with this equation, if you write out these pictures. So there would be some like A, B, C, and D in here. That's what we're doing. And so what is being said by this law is that this path from A to D and this path from A to D should be the same. Okay, that's what's being said. The question is, what does it mean to be the same? And the entire rest of the semester is going to be spent on saying what it means to be the same. So to foreshadow, just to whet your appetite, because I realize I'm maybe taxing your patience by giving you a lot of groundwork before I get to the real stuff. I have reasons for doing that. Let me whet your appetite of what comes in the future. What's going to happen is we can think of this as this picture as representing, as I use the words, two paths from A to D. And one way to think about this is to say they're equal is you can just say, well, you know, they're equal. Like, what do you mean equal? Equal is the diagonal relation. There's nothing to say. Those should be the same map. Well, it's not so obvious, actually, that that's the right criterion. But here's a way of picturing that's not so obvious that that's clear what that means. So one way to picture it is to say that if you suppress what's in the middle here, what I'm saying is that this can be thought of as a cell, which says that I have this boundary that says I have this path that goes from here, I have this path that goes from here, and I'm asking that this be sort of deformable into that, or that there's a surface, you could think of it, there are many ways of depicting it, that connects this edge to this edge so that they are the same by virtue of the fact that there is this information. So in particular, I could then summarize it. I can have a picture like this, and then I could write another picture like that. So I have a path in this case from A to D, and then I have some kind of a transformation that says this can be brought into that form and that can be brought into that form. That is a way of expressing what this equation is going to be all about. Okay? And this is that's a hint, whetting your appetite about the idea of higher dimensional type theory, because in constructive setting, you never talk about mere facts being true. You always have a notion of evidence for those facts, because everything is proof relevant. So rather than simply saying these be equal, what I'm going to say is that there's a deformation, which I might call alpha here, between the two endpoints, the FGH, this would be this kind of thing, and FGH is a particular thing, and that alpha is called an associator. Okay? So it's a particular witness to the fact that the composition is associative. Okay? So that's very much a constructive point of view. You never talk about things just being true. You talk about the reason why. That's the essence of proof-relevant mathematics that is being done, will be done all semester here. So this issue is going to come up now again and again, so I'll show you. So I just wanted to broach this subject. You're going to ask yourself, though, but if I have notions of evidence like this, then presumably I can also compose these with each other, and then maybe those notions of evidence are supposed to be equal by some kind of associativity law for these deformations, for these evidence. So, and that is indeed true. I might actually have an alpha prime here as well. And the scenario is stretched now, but I'm trying to ask you more generally. And then I can ask for a deformation from one to the other, also at yet a higher dimension. Okay? Which is a way of saying there's some sort of beta which says that alpha prime is equal to alpha in a weak sense, and each one of those is saying that this is equal to that, this is equal to that, etc. to infinity. Okay? I can do that all day long. Okay? There's no end to this. Okay? So that's the beginning idea, okay, of the homotopy theoretic interpretation of types, because what will happen is, as I'm going to show you shortly, proofs can be thought of as mappings, like this, and then we're going to talk about equality of mappings, and that's going to be spoken of in terms of what are called homotopies, which are deformations of one into the other, and then higher homotopies and higher and higher and higher and higher homotopies will be witnesses to these kind of equalities. And that's the connection with algebraic topology that has been discovered over the last few years. Okay? So that's a foreshadowing. So that's like whetting your appetite. So let's see how it works out now with the negative fragment. So I have to worry about my board discipline because there's a bunch of things I want to have on the board that I can't erase for fear, otherwise I'll screw myself up. So it will be very important for us to have these on the board, and I will assume you can keep this stuff in your head. Okay, so I'm going to erase. So what I'm going to do is I'm going to justify the props types principle by explaining the correspondence in terms of categorical structures. Okay, so we have this notion of a category. And what we're going to do is we're going to think of proof terms as maps like this. So in order to explain that, I have to tell you what this structure is. So let's look at a bit of categorical structure. So what is a terminal object or a final? It's sometimes called a terminal or a final object. One or the other. This is the easiest thing, like that. Okay, and it's often written 1 in a category. And it just says that for any, I'll write it out like this informally. Well, let me not use symbols. Let me write it like this. So for any object A, there is a unique map, which is written like this, from A into 1. Okay, different people have different notation for that. So in order to motivate everything, I want to be really clear about what is being said when I make statements like this. So first of all, what it tells us is that there is a map from A to 1. That's the first thing it tells us. Okay, so we'll write it like that. So there's, let me just, in this line I'll just say there's a unique map from A to 1. Let's write it like that. Let's give it a name. So the first thing is we'll give it a name. That's A to 1. That's the null tuple. And the second thing is we say if you give me any other map from A to 1, then it's equal to the designated canonical one that I just wrote down. So that's what for any A that you choose. Okay, so there exists a unique. And if you want, I could call that object gamma, and it would start to look pretty familiar. Okay, if I use the letter gamma here instead of the letter A, and then I would realize that that's just notation for gamma proof null tuple colon 1, and by the propositions as types identification, that's truth. So that's where this is going. Okay, so that's what you should feel. I'll just write down A, but you should think of the A in question as being your gamma. So that's what the notion of a terminal object or a final object in a category is. Okay, so immediately we see, right, this is the eta rule. This corresponds to the eta rule for truth under the identification of truth with 1. That is the idea that truth is a terminal object. So when I've written down logic together with these reduction and unicity principles, inversion and unicity principles, they're going to be enough to give me corresponding structures in a category. So let's look at the next one. So this is the part that corresponds to meets. This corresponds, by the way, to having a greatest element, okay, in a lattice. Because in an order theoretic sense, you don't have any interesting evidence, and you're just saying over here, A is less than or equal to 1. That's all you're saying when you're looking at like a Heiting algebra. So often in a Heiting algebra, the notation for the largest element is sometimes taken to be 1. People write it like that. Okay, so it's written like that. So that's supposed to be a 1, not a bottom. Okay, so you can write it like that. So I'm saying the same thing. And then there's no need for any idea of unicity because in a preorder, there's a degenerate evidence structure. Okay, so we do that. Okay, so now what happens with products? Okay, and the notation is going to be A cross B. There's a definition for what a product is, and what you say is for any A and B, okay, there exists, we could write it C, okay, such that we have the following data, okay. There's a map, we'll call it first, from C to A, and second from C to A, okay. And it's actually going to be better to write this thing. Let me write it the following way. Okay, so let me satisfying some further conditions. So I'm going to use a diagram. It's going to be better if I use a diagram. So let me write the diagram. Okay, so there exists an object. We'll write it C, which is written A cross B, such that the following thing holds. That what we have is Here's A cross B, that's my C. It comes equipped with a map to A and to B, like that, such that, now this is the part I need, it's the best such thing. So the terminology for this will be, it's a final span, okay, between A and B. That's what this is going to say. So think of that V thing as a span. That's called a span. A span between A and B is an object with maps that go from A to B. And I want it to be a final span. And what that means is, if you give me any other, let's call this P and Q, and I'll call them M and N. Okay, and I'll call C up here. So let's write that. Oh, I shouldn't have called it C then because I called that guy C. Let's call it D. Okay, M and N, which is written from here to here. If you give me any other span, there exists a unique mediating map like that, as they say, makes the diagram commute. That is, this cell holds, this cell holds. That is, all right, so let's write that all out, okay? So writing it all out, now I'll write what I started to write. You have a map from A cross B to A. You have a map from A cross B to B. Okay. Now, you have another thing that says, if you give me M, which goes from D to A, and you give me N, which goes from D to B, so you give me another span, okay, then there exists a unique thing which makes this diagram commute. Well, let's just first get the exist part. So the exist part is there's a map from D to A cross B. That's the exist part. Okay, and then there's going to be a uniqueness part and a commuting part. Okay, so given any two such things, there's this other thing which I might as well give it a name, because what I'm saying is for every M and N there exists a unique thing here. So there's you could say it's a choice principle, but it's really a kind of just quantifier rotation. It's not like an axiom of choice kind of thing. If I know it exists uniquely for any M and N, then there's a function underlying that takes M and N and turns it into that map. And so the function in question is the pair Mn. Okay, so the idea is that pairing, written like that, is the thing that takes these two guys and turns it into the mediating map that is guaranteed to exist. Okay, such that, and now some equations have to hold. First of all, so let's give this guy a name. Call it pair Mn. All right. So now what we say is that the diagram commutes. It means if I go here and here, that's equal to that. So that's in more algebraic notation says if I do second after the pair Mn, oh, excuse me, well, I did second. Why did I do that? Okay, how about if we do first just to be sane? Okay, so we'll do that, which is in A, and now we'll do second, okay, which is N, which is B. So these are our beta-like rules, okay? So these are beta cross 1 and 2 that are going here, because the commutation conditions, the fact that this part of the diagram has to commute, is expressed by saying if I do first after pairing, I get the first component, and if I do second after pairing, I get the second component. So that's what's being said here, okay? And now there's a uniqueness condition, and I'll write it out very explicitly as a uniqueness condition and then show how I can recharacterize that. So the uniqueness condition says, well, if you give me any other map, let's call it P, okay, which goes from D to A cross B, and P has the property that if you do first after it, you get M, and you do second after it, you get N, then P can be none other than the pair Mn. And this is from D arrow A cross P. Okay, and this is in disguise, the eta axiom for cross. This is a uniqueness condition. Okay, so this is the existence condition. There exists a pairing which has these requirements, and moreover, anything that meets these requirements can only be that pair. So here's a way of depicting that. What we're saying is, if you look at it, is there's a little bubble here. What we have guaranteed here, I'll write it with the dashed arrows because it's exists by the definition. So we're guaranteed to have an Mn here. So that's the one I mentioned before. And we're saying if you gave me any other one which mimics the behavior of M and N, it makes these two cells commute, Okay, so P first is the same as M, and P second is the same as N, which is the requirement that the pair satisfies. Then these maps, well, are at the very least deformable into one another, or they're equal. So the uniqueness says that if you seem to have two things that act properly, there's really only one there.
Excuse me.
Okay, they're equal.
Right.
Yeah.
So you've got first composed with Mn equals M, and then you've got A. Should that be D to A and D to B rather than just A and B?
Did I make a mistake there?
I think that because they're arrows in the category.
What did I do? Okay.
So you've written just A.
It would be just like me to
D to A and D to B.
first composed with M. So M is of type A. Oh, D arrow A. Yeah, sorry. Yeah. Thank you. Yeah. Because I get used to the type theory notation where this ends up over on the left over here, and then I forget to write it. So thank you for saying that. So it's a map from D to A and a map from D to B, and then this one I happen to do it right. Okay, so we can do that. Okay, yeah, sorry about that. Yeah, so in the type theory notation, you end up writing D proves, you know. Okay, so that's why I did that. Okay, yeah, sorry about that. Okay, so yeah, so that's the definition. Okay, so this is the notion of the uniqueness of that map. Okay, so that's what we're doing. Okay, so now let me say something else about the uniqueness of that map because it'll connect it up with the syntax a little bit better. Okay, which is, if you look at what's going on here by a simple congruence principle, right, we have M is equal to first of P. So this is telling us that first composed with P and second composed with P, this pair is equal to P. Okay? That's what we're saying here. Because M and N are respectively first to P and second to P. So let's write them in. So I get first composed with P and second composed with P, and that is going to be equal to P. Okay, that's what this equation is saying. So that is very now similar to the condition, oops, I'm pointing to the wrong one, this one, to this condition written over here. Okay, that is the way to see that. So we're writing it out. Another consequence is another thing that we can get out of this is the following idea. We can write this as saying the pair first second, like this, is equal to the identity. And we can get that if we take M and N and I compose that with P, then I can say that that is M composed with P and N composed with P. And those two things are enough. Because, right, now if I take, the idea is that I can take first to P composed with second to P by this equation, right to left, pull the P out, and then turn this into the identity, and then I'll get identity composed with P, which is P. Okay, so this is another way of writing it. So this is a way you will often see, okay, written, the notation you will often see in many sources as to expressing the uniqueness of that map as given by these equations. Okay, so that's the thing I wanted to mention to you. So what is going on here is it's telling you something about the behavior of substitution. If I substitute into a pair, that's what the composition is representing. If you look at the rule of transitivity and what that is, that's the principle of substitution. Then it says you substitute into the pair by substituting into its components. Okay? That's what's being said here. Okay? So that's what's going on here. And then this is, in some sense, the essence of the uniqueness principle, because it just says if you take something, project it out, and put it back together, you get the same thing that you started with. If I take, so you can spell that one out by saying, well, it's what this says, like that. But it's essentially just saying that in the most general sort of way possible. This would be a map from A cross B to A cross B. If I tear a pair apart and put it back together, it's the identity. Okay? That's what's going on. Okay, so my point is that this is like really saying as plainly as possible the uniqueness condition. If you give me any other one that behaves this way, it's the only one. But if you mess about with it a little bit, you can write it in a simple form like here, and then it looks exactly like the eta condition that Gensen wrote down. So there's a remarkable confluence of ideas here because these were developed quite independently, and it took Lavier in the 1960s to really notice the exact connections that I'm describing now. Lavier and Lambeck to develop these ideas. Okay, so that's the and then the exponential part. Okay, so now there's a notion of an exponential. So now I always have a board discipline problem. I want to leave those up, so I'm going to have to erase here. So you're with me so far, I hope. Then I want to say something about coproducts and a cool little observation that connects them up with BDDs, if you know about BDDs. So I'll do that. Okay, so now exponentials. Well, I'll draw the picture then. So this will be written b to the a. Okay? So the idea is, first of all, there's, let's see, let me think about how I want to depict this. I will do it, let me see what I wrote in my notes. There's different ways of writing down the, there it is, like that. I wrote it like that, okay? So there's a map here. So this is called application. Oh, sorry, that should say A to B. So that's called application. All right, so the first thing is, for any A and B, there exists this object, B to the, which we'll write B to the A, okay, which comes equipped with a map that says you go from B to the A across A into B. So that's called application. But it's universal amongst such things. That is, if you give me any other object C and a map, let's call it H, which goes from here to here. So if you give me this scenario, so one way to think about this is that one way to think about this is that something that's kind of behaving like a function, that when I conjoin it with or pair it with A, there's a map that turns that guy into a B. There's a transformation that says if you curry this, that's what I'm really expressing is what currying is if you curry this, it says given C, it can turn it into an A to B. If H is such a thing, then it's going to factor through this guy, which means that there exists a unique map here, which is written lambda of H, which goes from B to the A, such that, and now there's a notation that people use here, it's usually written lambda of H cross the identity, which at A, which is just notation for lambda of H composed with first, and the identity composed with second, which is just second. Written like that. Okay? Such that this diagram commutes. So this is unique, and this diagram commutes. Okay? So we have that. So it'll take you a little while if you've never seen this notation before. It'll take you a little while to see what's going on here. But the intuition about it is, right, that there's an environment going on. So what I do is I plug in the environment and I plug in the argument. So this represents sort of the environment and the argument, and I plug that in, and that gives me H, and I plug that in and I get my B. Okay, so that's what's going on here. So this is the function and its argument. Okay, so that's what is being expressed here. This is application. It's like that. So if you then write that out in syntax, okay, what we're saying is the following thing. We're saying that, well, first of all, this diagram commutes. So we can say lambda of H cross the identity, okay, app composed with that, which is app after the pair lambda H after first and second, if I do that right, we're saying that this is equal to H. So that's the first requirement. Okay, that's the commuting requirement. And then the unicity requirement says, if you give me, am I doing this right? Yeah. Okay. And then right. And then it says, if you give me anything else that behaves like that, so if you give me app with, I don't know, since I was calling that H, let's call this G. Let's say G composed with ID is equal to h, then it's unique. Then we know that g is equal to lambda of h. Okay, that's the uniqueness part. So if you give me anything else that behaves like this, so that g cross id, right, behaves when applied, gives me h, then these two maps are the same. Okay, that's what is being expressed here. That's the uniqueness. Okay, and if you cock your head around that, okay, and if you look at that with a little notation, then what you will end up with is exactly the eta rule, okay, which is going to, if we plug this in, so if we take h as this, so what we're saying is lambda of, now plug this in, app of g composed with, or lambda of h, excuse me, app of lambda of h cross id is equal to, is that what I want to say? No, what do I want to say? Take this guy, plug that in, lambda of, all right, what, pardon me, let's start this over again. Okay, so we know that app composed of g composed is h, so I want to say is g is equal to lambda of h, which is app composed with g cross id. Okay, so if you expand that out, what the cross means, that says if you do an application with the pair g composed with first, that I call it, yep, g composed with first and second, okay. So the idea is that if you just apply g to its argument, right, that's what's going on, and lambda abstract that, then you're going to get the same thing back. That's the idea. So this is expressing the eta principle for the arrow or the exponential. Okay, it's written like that. Okay, question, Vonia, what's the matter? Oh.
Yeah. So I'm looking at this diagram and having trouble figuring out what the quantifications are. Like,
Okay.
For all something. What is universally quantified? What is existentially quantified? What is, you know,
Okay.
the,
Yeah, let me just make sure I didn't.
one thing exists, the other thing.
Yeah, L is equal to lambda of m. Yeah.
I see the diagram, but I have a hard time putting that all together.
Yeah. So the idea is saying the exponential is characterized by saying it comes with this structure. It's got this app which goes from b to the a across a, which is universal among such things. That is, if you give me some other thing, h, which goes from c cross a, arrow b. So if c is a pretend exponential object, okay, then it factors through the real one. Okay? Factors through means there exists a map from c to b to the a. So if you think in terms of preorders, it means that c implies or entails b to the a. C is smaller than b to the a.
So b
Okay.
I'm thinking of b to the a as a function.
So,
Think of C
yes,
as
that's
a
right.
function, and what's the relationship to b to the a? The function b to the a.
What I'm saying is, if you think of this as a logical entailment, what I'm saying is that C entails b to the a. It's a proposition that's stronger than a implies b. Okay? Because it's stronger than a implies b, because it behaves like it. That is, if you take it and conjoin it with a, I'll be able to get a b out of it. So something that I can conjoin with an a and get a b out of is something that is has at least as much information content, if you will, as the exponential. So in terms of preorders, the exponential was the largest thing which has this quality. So we say this is just a less than, and we end up saying that this is less than that. That's what we said earlier. So that's the exponential in a Heyting algebra. Here I'm just filling in the data that says, well, it's not merely whether it's a fact or not, less than, but giving you the reason why. So if here's the proof that C behaves like an entailment, like a function or like an implication, if it behaves like an implication in the sense that when conjoined with A it gives you a B, then it must factor through the implication. There must be a map from C to B to the A, which makes this diagram commute. That's the idea. And so that map is written like this. This is the map here that's uniquely given, and the diagram that commutes is lambda of h cross the identity. So what we're doing here is just saying the identity here is just playing the role of just saying the argument doesn't change. Okay, I'm really capturing the idea that there's a map from C to B to the A, and then the argument doesn't change. When applied to the same argument, that's what's going on here across the identity. Lambda of h behaves like this guy. I mean like G, this putative other guy. Here, I wrote G here. That should be H. No, I'm sorry. I'm right. Yeah, no, I'm right. Yeah, if you give me another one, another such map is unique. There's a uniqueness condition as well. Sorry, I'm getting myself confused. Okay.
So is there an intuition for why you're calling that map lambda of h? I mean, I was thinking of that.
Yeah, because that's what it's doing. It's lambda abstracting. Because what's going on here? This is basically saying gamma xa proves h is b, and then I'm turning that into lambda xh, which is b to the a. I mean, that's what's being done. Okay? That's the essence of what is going on here. Okay?
The arrows are like turns.
So the arrows are like turnstile. Yeah. So what I was saying, I said this before. So we're going to, we can make this completely precise. Well, I can do it right now. So the idea is that there's a correspondence between this and maps, and I'll write gamma bar here to A, written like that. Okay? In order to explain what this is, remember what I did with Heiting algebras. So with Heiting algebras, what I said is there's a correspondence between this and gamma bar being less than or equal to A, where this is the meet A1, the meet AN of all of the assumptions. Okay? That's what we talked about with respect to Heiting algebras. Okay? So with categories, what I'm going to do is this is going to be, by definition, the product. And I'll left associate it. Everything I'm doing here is done so that the last variable is sort of most easily accessible. This is what gamma bar is, and we have a map M from here to A. And the idea is that variables then, when I look over here and I look at variables, so in particular, let me write it up here. What are the variables? Well, if I look at the last variable, so I have xa, xa by reflexivity, that corresponds to gamma cross A goes by second to A. And then I can say, well, if gamma gives me, let's call it yb, then gamma with xa gives me that y is b, something like that. So you can think of this as look up y inside of gamma and find out that it's b. I'm going past the x here. So what I'm doing is I'm basically saying I'm going to do a composition. What I say is that if you can find a variable, which is, let's call it a path p, which goes from gamma to b, then by composition I can put on a and I can do p after first to give me b. I take the first thing, so that goes to gamma, and then I do p after that to get me to b, and that's the composition. So the idea is that a variable over here turns into second of first to the n, well, composed with first to the n of something, well, composed with first to the n. So you do a bunch of firsts to put her down to get it, and then second to get the guy. And these are called de Bruijn indices. Okay? So these are called de Bruijn indices. That's the notion, because de Bruijn introduced them, or the name-free form. Because the idea is that instead of having, so if I have x1 through a1, xn through an, gives me, xi is in a. That's the named form. I can refer to it directly. In de Bruijn form, what I would say is I have a1, a2, cross, cross, an, tells me that, well, now I have to do second Well, and if we think of that as having one variable, just call it x, which is the environment, then I'm doing second of first as many times as necessary of the environment, x. Okay? And so that is just the number I, the de Bruijn index I. If this is the I, if we're looking at the ith variable, if we want to get the ith variable here, and I do I compositions here, where I probably have an off by 1 error here somewhere. Maybe these should be 0 to n minus 1 to make it all work. But anyway, the idea is that you quitter down this product to project out the variable that you need. And the number is all you need to know. Okay? So the number I, so every variable can be represented. You don't really need the names mathematically. You can just say, instead of having this guy, what I do is I just say, oh, this says the de Bruijn index I is of type A sub I. And then you suppress the variables entirely.
It should be numbered from right to left instead of right to left.
Yeah, maybe I should have numbered them the other way around. Yeah, okay, sorry. N minus 1 down to 1. Okay, yeah, sorry. Yeah, that's what I should have done. Okay. I knew I was going to get something like that wrong. Okay, note takers, this is what you have to fix up. Okay, sorry about that. Okay, write it like that. And then the ith thing, the first variable, second variable, etc., is obtained by taking enough first projections and then the second projection, and that's the guy. Okay, that's how you do it. So that's the notion of de Bruijn index. And that arises out of the categorical structure. And it matches up exactly with the interpretation I gave you earlier of a Heyting algebra in terms of you take the meets of all the assumptions and show that it's less than or equal to the conclusion. That's the relationship between entailment and the pre-order structure in the algebra. Well, here the relationship between the proofs and the maps is mediated by this interpretation of variables, and then the proof theoretic syntax is mimicking the syntax of the category, of the structure of the category. So we have products, finite products and exponentials, okay, written like that. Okay, so that is the correspondence. So what I want to do next time, I thought I would get to it today, but I didn't. What I'll do next time is I'll just look at the positive fragment, so I'll add in sums. So that gives us coproducts. And the uniqueness principle will turn out to be a generalization of what is called the Shannon expansion. If any of you have studied BDDs, binary decision diagrams, which are used in Booleans, in the two-element Boolean algebras. Okay, it turns out have a complete generalization, which is expressed as the uniqueness condition of case analysis, and that will be generalized the notion of the Shannon expansion, which arises in BDDs, binary decision diagrams, if you know about those. Okay, so BDDs are specific to the two-point Boolean algebra, the one that you learned in school, but it turns out the concept is much more general than that. Okay, and so I will show that next time. Okay, so that's where we are. If you want, to look at the background on this, you can look at the best source I know is Steve Audi's book called Category Theory. That's the most accessible thing. It's called Category Theory, and it's a book actually that's about category theory, surprisingly enough. And it develops all of this connection, the connection between logic and categories in the way I was describing. So I'm not going to spend a huge amount of time in that. I could spend the whole semester doing this in detail. So I was kind of assuming you've seen this sort of thing before, but maybe not. Okay, so, all right, so that's the message. So the message is, at least in conjunction with the unicity principles, and I'm going to look at the status of these things in detail later, because whether these should be definitional equalities is a question, okay, that will come up. We'll talk about that later. But at least as a first cut, the inversion principles and the unicity principles give rise to show that the propositions, together with their proofs, taken modulo this equivalence that I'm defining, has the behavior of products and exponentials in a category. So that's what justifies the sort of propositions as types correspondence, is that those things completely fit together. So that was my doctrine of Trinitarianism that I told you about on the first day. So we have category theory and proof theory, type theory working together, and I'm trying to show you how that all goes. Okay, so that's what we've done so far for the negative fragment, and then next time we'll do the positive fragment, and then I'll revisit that issue of normalization. But it's not next week, it's week after next. Okay, thanks for your attention.